So today it is my pleasure to introduce Yan-Fei Jiang, who is a research associate at the CCA, but he is absolutely no stranger to Princeton. You completed your PhD here in 2013, working with Jim, and also live nearby here as well. So very much a local in that sense. And you've been the recipient of a number of prestigious awards throughout your career, including the ITC, Einstein, and KITP Kavli Fellowships. And that varied award list is also complemented by your diverse range of interests. And you're an expert in developing and leveraging a number of numerical techniques to investigate a wide range of astrophysical problems, ranging all the way from disk accretion, stellar evolution, and a number of radiative transport problems, some of which we will hear about today as you're telling us about radiation and magnetic fields and AGN accretion disks. So the floor is yours, Yan-Fei.
Thank you for the invitation. I think I know many of you already, so I think that today I just want to discuss some of the work that we're going to finish soon, particularly discuss the role of radiation support and the magnetic pressure support in AGN disks, and also try to propose a new mechanism to explain the soft X-ray access, which is quite common for many AGNs, based on the simulations, which is something we do not anticipate before we do the calculations until we see the result, and it's more like an exciting numerical experiment. You finally see something and you realize that this seems to be reasonable. So I try to just give you a rough overview of the observational properties for AGNs and what exactly the soft X-ray access. Before I go to all the models, I try to also describe the standard thin disk models and also some other models to overcome some of the difficulties. One particular question I try to discuss is in the numerical simulation, particularly on what conditions the disk will become radiation support, and in the classical models, on what conditions you become magnetic pressure support. And one key point that I try to make from the simulation that with the theories, the numerical calculations can give you a wide range of accretion disk models. And you can argue that your favorite model always explain the observations. But I will say the spectrum, that no matter what model you have, just give out the spectrum and see whether your spectrum can actually match what we see. And that will be actually one key and powerful tools to distinguish some of the models. And then particularly one point I want to make that the Bound constant that happens in the disk could be a natural way to make the soft X-ray access. Okay, so just one big background, I think I probably can skip this. So AGN is what interesting for itself. There's so many AGNs observed across the different scales. They have play a very important role. But also nowadays, the AGN also make like kind of like when you cook, it's more like an ingredient. You just put it everywhere. You put the AGN at the background, and you make stars, you make fractals, you make everything you want, and you can generate all the interesting stuff. But I think one key aspect of many of the problems that you need a AGN as your background model to begin with. A lot of predictions, properties, depends on actually what is the AGN disk model you put in, right? All the thermodynamical models, the favorite is, of course, for the upper disk model. Even though that may not be the right one, but that is the most easy thing that you can do. Okay, so that's just a very brief background on the properties of the AGNs. I think I always like that if you actually, before you do simulation, just think about that. Just give some rough estimate before you actually jump to the simulations to get an idea of the basic properties that you actually expect from such AGN disks. So one characteristic properties of an AGN disk is, of course, its luminosity. Just take the characteristic Eddington luminosity and take the black hole mass. And one assumption you just need to make is that if the gas and the radiation are thermalized, you can ask what is actually the characteristic temperature you expect from the disk. You do not need to actually assume any detailed assumptions in the disk, just say the thermal emission from the luminosity, the Eddington luminosity, and the emission area, just take the characteristic structural radius of the black hole, which only depends on the black hole mass. Then you will find that for 10 to 8 solar mass black hole, you will have a temperature like around 10 to 5 K-ish. If you go to star mass black hole, you will go to 10 to 7, 10 to 8. So this is a very genetic, as long as you assume the gas and the radiation are summarized and to get the Eddington luminosity. So this is kind of typical temperature you have. And another important quantity, of course, is the density that you expect for the flow, which is the more subtle, because the density, of course, you will give you mass accretion rate, then depends on the inflow speed. If you say your inflow speed is some fraction of the gas sound speed, then you will get a density in the order like 10 to the minus 9, 10 to the minus 10 gram per cubic centimeter. So this just give an idea that you conditions you expect for AGNs. The standard synthesis model is actually just based on some of the assumptions, like assuming the disk is optical thick. The radiation basically will balance any dissipation that happens in the disk locally. The inner part, if you go through this, will be radiation supported, and the outer part will be gas pressure supported. And the disk is optical thick, as required if you want the gas and the radiation to be summarized. So there are some very basic assumptions that you really need if you want to construct a thin disk model. The only assumption that is very crucial for the thin disk model is that you, of course, need to assume the viscosity, and you assume the stress is proportional to the total pressure. And that will give you very nice properties. And that, I think, in my opinion, that is the reason the disk model is so popular. The density, the pressure, everything become power laws of the radius, some dependent on black hole mass and accretion rate. And you have a model that you can use in any of the contexts you like. Even though the model is so simple, but it's not too bad actually. If you look at the typical spectrum for AGNs, even collect quite a while ago, the characteristic feature that you always find for a lot of AGNs that you have is a so-called big blue bump, and then the other infrared bump, and then the part that also often is the hard X-rays, and then there's another component that I will talk more, the so-called soft X-ray access. So the big blue bump, if you look at the frequency, the horizontal is the frequency. It's basically for like a quasars. It's around like, for example, the kind of 10 EV-ish regions. Much easier to see here. So if you convert, say, EV, like 1 EV, if you can convert to thermal emission, that's roughly 10 to 4. 10 EV is roughly 10 to 5K. So that is another reason, even though the thin disk model may not be right to explain all the features, but the fact that the model gives you roughly the big blue bump in the right frequency regimes tells you it cannot be too wrong. For example, the disk probably is optical thick, at least for the part of the regime that you emit all the big blue bump kind of photons. So the soft X-ray access, so that is the part of the, if you're not familiar, so the definition is that for hard X-ray photon, for example, for photon about keV to 10 keV, and that is typically believed to come in from the inverse Compton or corona on top of the disk. But if you actually take if you just try to extrapolate the power law spectrum shape of the hard X-rays and go to low frequencies, and for the other data like UV data you can get, and you fit the disk part, you will find that there's always the photons in the frequency range between like 0.2 keV to 1 keV. That is way above the kind of X-ray flux you expect based on the power of the hard X-rays, and also is above the spectrum you expect from the disk. And that is basically because the typical disk temperature from the is around like 10 to 5K to 10 to 4K, and that can contribute this part. But then if you want to get a thermal emission in this soft X-ray, like 0.2 to 1 keV, you will need like a gas temperature 10 to 6 K and above roughly. But then it's not the same inverse Compton as the corona, because the corona shape is not the same as this more like a thermal-like kind of a spectrum shape. And this is very universal. A lot of samples that you see a spectrum shape turn over from this kind of UV part, and they do not connect directly the stem shape and the hard X-rays. And even more recent data, this is particularly prominent in the so-called narrow line C41 galaxies. Narrow line C41s are kind of systems around black matter 10 to 7 with accretion rate close to Eddington-ish. And the soft X-ray photons actually have a much larger luminosity compared with the hard X-rays that you believe coming from the coronas. So it's always a pattern like where this kind of component is coming from. There are quite a few interesting features of this component. One component that, of course, for people to fit in for the data, if you do not have a model, you always just fit a black body, right? But one black body doesn't fit, you have two black bodies. You just had an additional component. And normally people fit just have a multi-temperature black body for the low frequency part. And if you try to fit a black body shape to the soft X-ray, the kind of temperature you need to fit this component is always around like 0.1 to 1 keV-ish. And this temperature is very interesting. It's not sensitive at all to the black hole mass and the accretion rate. That means if you try to look at this component to like 10 to 8 solar mass black hole quasar, or 10 to 7, 10 to 6 solar mass black hole like narrow line C41s, they always show up in this kind of frequency range, and with a black body temperature fit around this kind of value. So that is actually quite surprising, because if you expect this kind of thermal emission from the disk, normally you will expect that everything will scale with black hole mass, for example. The typical, yes.
What about the fraction of the luminosity in this soft X-ray?
Yeah, that will vary as a function of m dot, actually, typically. For example, the narrow line C41 typically has a much stronger soft X-ray.
Like what is it? 1%?
The total luminosity?
Yeah.
Total luminosity, I don't know exact. I think maybe like a few percent. Yeah. But also actually a factor few larger compared with the hard X-rays from the corona emissions. If you want to produce from the thermal emission, as I mentioned, the typical disk temperature too low to actually get the spectrum. Another property that people think that may happen, for example, thermal Compton, right? As you will get from the hard X-rays. Hard X-rays typically come from the inverse Compton or gas temperature like 10 to 7 above. Maybe you have a separate hot gas with a temperature like 10 to 6 or above that you give this soft X-ray. But then if you want to actually match the spectrum shape, again, not only just get this, but you want to match the property of the shape that you see here, as I will discuss later, you need to tune your parameters to get that. And the reason is that the thermal Compton will give you a shape actually depends on the so-called Y parameter. I will define that later on. And if you want to get this, roughly you want a Y parameter coming from optical depths like 20 to 40-ish. In one sample, like given by Chris Stone's paper, you need to like 47, she even put. I'm not sure how she get that, how robust that is. But that just tell you, you need the optical depths definitely more than one. In order to get this something like thermal-ish spectrum, but not really black body. So how do you actually get that conditions? And also one interesting part is that people always think that the AGN disk is just a scale-up version of X-ray boundary disk, right? You can scale every property from the standard mass black hole to AGNs, so everything just scale with black hole mass, temperature get lower, but that's not quite right, because if you actually do the same thing scale to the standard mass black hole, the standard mass black hole disk, you can actually beautifully fade the spectrum with a multi-temperature black body plus one inverse Compton hard X-rays. You do not actually see this kind of a soft X-ray component in between the disk part and the corona part. So that is also a little bit puzzling, like what is the special about the AGNs that you see this component, but not in X-ray boundaries?
Are we sure about that? Because, you know, this component is like all absorbed, right? I mean, if you're just inferring it.
For AGNs, yes. For you only see like this part, you have a lot of emission.
But even in the galaxy, I mean, wouldn't everything be absorbed?
For X-ray boundaries?
Yeah, for like in this, you know, hard UV band.
Oh, X-ray boundaries, they are not in this part. The disk emission is not in this part.
Yeah, no, it's to the right of it, yes, but I mean, I'm just trying to say that you don't actually observe any emission coming, you know, at the range of like around 100 eV.
Oh, this is the correction for absorption. So yes, the true observed data will have a lot of absorption for this part.
Yeah.
But people have I mean, I'm not an observer, but have models, like how do you account for the absorption? And then this is on a thought. But if you question that, because they have a lot of objects that show this feature, which seems to be very robust. Like the doesn't depend on the you cannot completely get rid of that. I think that's the way to say that. Yeah. Okay, so that's some very brief summary of the observational part. We'll come back to the theoretical part. Of course, if you want to use the standard physics model, there's a lot of issue with that. And one issue is the thermal instability. The inner part of the disk is thermally unstable. And I basically did my thesis with Jim to show that it's real. It's not something that just happens with a disk model, because even if you have some radiation supported with the MI turbines, you could still have this instability. But then a lot of alternative models have been proposed that may fix some of the issues, and you may get different disks compared with what the standard physics model will predict. And one of the models is that you may think that the disk is actually supported by magnetic field, not by thermal pressure. Of course, we know that the MI is important for angular momentum transport, so you need a magnetic field to begin with. But in those models, they actually argue that the magnetic field is not only responsible for the angular momentum transport, but actually you build up strong enough magnetic pressure that you support the vertical gravity of the disk. It actually starts from very early on. They have proposed that there may be different mechanism to amplify that. And the one question is always that the magnetic field will typically dominate by toroidal component in the disk. If you have tried to use the magnetic field to actually balance gravity, it's typically unstable. It's very hard to maintain the structure with the magnetic field, for example, the Parker instability. So this kind of disk is intrinsic, will suffer a lot of instability. And one model, this comes from the actually Compton and the Uni-Levin's paper. Maybe there is a statistical balance. For example, you have a toroidal magnetic field, and then you could have Parker that the bond right up, and then the gas that originally supported by the magnetic field will fall in toward the disk. But once you get fall into a disk, your magnetic field will get sheared. And then with the shear magnetic field, it will generate some radial component. And that can generate another toroidal magnetic field because of the disk. So maybe you can close the loop, get some kind of turbulence to sustain the magnetic field. So this idea has been proposed for a long time that something like this may happen, and has been observed quite a few simulations that in principle you can do this with either toroidal magnetic field or strong enough toroidal magnetic field to begin with, for example, in those recent papers. So the question is always be like, if you now rely on magnetic field to support the disk, what is actually saturation state of the disk? Like how the magnetic field, if you have this kind of dynamo, how that will saturate? So what determines the Affin speed at the end of the day in the disk? And another big question, of course, like where the magnetic field coming from in the disk that you can sustain the disk itself. But people can go actually very far along this idea sometimes. So this is, I'm sure you already know, I think the Phil Hopkins gave a talk here. So they have been also suggest that if you start with the galaxy scale simulations, all the way zoom in to like gravitational RG radius, you actually find that the disk is a strongly magnetic pressure support. And this is the most recent paper. They actually show that this happens even when the accretion rate is a few percent anti-accretion rate. So this is the model. I believe this is like a few anti-accretion rate. This is 30%. This is 3% of the anti-accretion rate. This plot is showing the optical depth in the disk in their case, and the bottom plot is showing the gas temperature in the background and the radiation temperature in the line here. So one thing, well, even though it is claimed that this kind of model can explain everything of the AGNs, including the torus and the emissions from the inner part of the disk, but a question that I always have is that this is fundamentally quite different from the thin disk model in the sense that for a few percent anti-accretion rate, the optical depth called the whole disk essentially become optical thin. If you look at those this model, like a few 3% of the anti-accretion rate, and look at the optical depth in the disk they formed, this is actually below 1 across the whole disk. And if you look at that is the consistent. If you look at the temperature of the gas and radiation temperature, the gas temperature has a wide range from like 10 to 5 to 10 to 8, 10, 9. The radiation temperature is only like 10 to 4, a few times 10 to 4. So they are completely, essentially, they're quite different. They're not thermally coupled for the gas and radiation, as you will need, right, for the disk that is not optical thick. But this is, again, as we estimate early on, right? If you have a not optical thick disk, but optical thin disk now, and this happens because in the magnetic pressure support disk, the inflow speed is very large. So that reduces the surface density. If you actually carry a spectrum, right? The spectrum, I said that is actually important. If you want to produce the spectrum of the AGNs, I'm not sure you can actually do that with such a thermal conditions of gas. And that is the key point that I try to show that if you, no matter what the disk you get from the simulations, it's important to keep the spectrum in mind. And before we actually calculate the simulation, you can easily again do an order of magnitude estimate. If you take the accretion rate, which again doesn't the real rate depends on any of the disk model that you assume. The accretion rate is just a surface density, right? Multiplied by the radial inflow speed. And if you take the optical depth, say electron scattering as a characteristic value, so optical depth is just kappa times sigma. And you put the characteristic as an accretion rate. And if you inflow speed really reach roughly the free fall speed, for example, as happens in some of those magnetic supported disk model, you will find that for Eddington accretion rate, you are unavoidable, your tau is 1. So that means that if you drop below Eddington accretion rate, your tau will basically become smaller than 1, if that is the case. And that's why, right, in the thin disk model, the inflow speed is way much smaller compared with the free fall speed. So your optical depth is much higher than that.
That's simply because your kappa is cancelled in your equations. Why you have?
Yeah, this is because of your definition is based on the electron scattering optical depth, and free fall speed is basically cancelled everything. And this target 1 is the roughly independent black mass, and does not change so much with the radius. So I think that is very I think it's a very strong constraint that sometimes you cannot push too far if you're too strong magnetic pressure supported. Another big question that is always in mind that in the magnetic pressure support disk, actually what determines the vertical structure of disk, which is also a question even your disk is radiation pressure supported. And that is because if you look at the momentum equations of a disk, steady-state disk in the vertical directions, right? If you just take out the momentum equations, will be the gas pressure gradient, radiation pressure gradient, and all the magnetic field terms. And the vertical gravity basically low because Z in the disk context. If you are gas pressure supported disk, which is the case, for example, in planar disk, which is very familiar for many of you, because if you take isothermal, the gas will be low T, and T if it's a constant, take that out. And that hydrostatic equilibrium will basically constrain the density profile. But you cannot do that if you have actually magnetic pressure and the radiation pressure. And the simple reason that the radiation pressure actually T force, that density does not enter directly. And the magnetic field, of course, equation state magnetic field does nothing tell you what the magnetic field should be for a given density. So simply coming from the hydrostatic equilibrium do not actually tell you what the vertical structure of the disk should be. So at the end of the day, actually turned out is actually the thermodynamics is play a very important role to determine the vertical structure of the disk. And essentially comes in the dissipation. Where the dissipation happens and how strong the cooling is will change the vertical structure of the disk for both actually the radiation supported case and the magnetic pressure supported case. Okay, so that is actually more long motivation in some of the estimate and the thinking before we go to the simulations. So before I describe the setup, I just want to just give you a rough idea of the characteristic scale and in the AGN disks. For example, if you take a 10 to 8 solar mass black hole, it's generally expected if you do estimate the temperature, the X-ray is typically coming from like 20 RG-ish. The UV typically coming from region between like 20 to 100 RG. And then the optical is typically coming from the much further out, just based on the conversion from the wavelengths to temperature. And the characteristic time scale is like half a day from the inner part and go to a few days to a few months in the outer part. So the before you can, I mean, ideal you can do just put everything, just simulate all the scales in one systems. Maybe possible in the future, but in the past few years, so we have taken the approach that you really have a similar different radial range from the inner part and then from different outer part and get idea of what the disk will be. And another reason that is interesting to do that because it's unlike MHD simulations. MHD is scale free, right? If you do MHD, unless you do GR, and then the simulation is the same. Inner boundary is 1, the outer boundary say 10 or 100. It doesn't matter like where you are. But then if you actually put in the radiation, you cannot do that because the temperature is different. The ratio between radiation pressure and the gas pressure is different. The opacity is also different. And the kind of optical depth conditions that you will have from the inner part and the outer part will also be quite different. The kind of simulation that we've been trying in the past is that we focus on the radial range from the 50 RG and the outer part. And the numerical experiment, we start with a torus, which is located about like a few hundred RG to supply the mass and magnetic field. So we chose this essentially so that we do not want to put any disk in the inner region to begin with. So we want the gas to flow in and to form the disk so consistently. And we tried two different kind of magnetic field configurations. The single loop case and double loop case, which essentially say that if you have a magnetic field, follow the torus, which is the single loop. The double loop is that if you have one loop of magnetic field on top and another loop with the opposite sign below. And the main difference because the MI depends a lot on whether you have this net product magnetic field. For the simple loop case, if you accrete the gas or magnetic field, you have a net product magnetic field. For the double loop the case, then there's no net product magnetic field across at least the midplane. Another very important difference that how do you actually get different accretion rate in this case? In addition to the kind of the magnetic field, another important difference is what is the surface density you put in the torus. That is basically quantified by the optical depth tau parameter across the center of the torus. Typically, what we'll get is that if the density or the optical depth across the torus is high, the kind of accretion rate you get from the inner part is larger. The lower the surface density you put here, basically the field of the mass you supply, then the accretion rate you get will be lower. Another important thing to keep in mind is the opacity. So if you are, because you are doing radiation MHD, so you are doing the transport of the photons, the coupling between the gas and the radiation depends crucially on the opacity. So this is the opacity we use for the AGN case. So this is the so-called loss mean opacity as a function of temperature. Because the temperature regimes, right, we estimate between a few 10 to 4K to 10 to 6K, and each line for a constant density. So you can see that when the temperature is high enough, for the loss mean opacity, it's basically electron scattering. And when you go to lower temperature, you have the bond caused by the ions, and also the different temperature opacity caused by the heliums, and which can be actually much larger compared with the electron scattering. And the opacity features are also temperature dependent. You usually have this feature around a few times 25K, which is also the region, if you remember the temperature we estimated for the optical UV blue band. It's basically like the 10 to 5K is roughly like 10 UV kind of regimes. So this is also the region all the opacity actually come to play. Okay, so I jump directly to the 4 simulations that we have. So start with the very similar initial conditions, but with different choice of the density of the torus, the magnetic field. So the top 2 panels are the 2 cases with a single loop. That means we have a net product magnetic field across the disk. The bottom 2 panels are the case with a double loop, so there's no net product magnetic field through the midplane. The label just indicates the final mass accretion rate that you get. So this one get to about 3% antenna accretion rate. This one get to about like 4 times, and this one with the double loop get about 6.60%. This about 3 times. So you can see the kind of variety of a disk you end up with the choice of the mass density and the magnetic field. Just a few comments that for the case with the net product magnetic field case, this one has a strong magnetic centrifugal June wind, which is similar to a lot of isothermal simulations that people find. But even with the net product magnetic field, when the accretion rate is low, you actually do not get a very strong centrifugal magnetic field. Basically, this is showing the density at the snapshot and slice. So you can see that the black line is showing the magnetic field streamlines, and the white contour showing the velocity distributions. So you can see that you want to get the wind, you not only need the product magnetic field, and actually you only happen that when the disk is relatively thick, so the accretion rate is high. For the bottom 2 panels, you can see you really only remember the initial magnetic topology in the funnel regions, but you still get very turbulent flow inside the disk. You can see even some kind of like eddies inside the relatively thick disk. Another very interesting feature, if you look at the density distribution of the colors, you always get a very dense layers near the midplane, even though I will show later all the 3 rounds are magnetic pressure supported. And the last round is actually radiation pressure supported. And if you look at the density scale height did get larger when the accretion rate is higher. But the region where most mass is actually the much thinner layers for the lower accretion rate. And that because the cooling is much stronger. The cooling can basically determine the disk scale height, as I explained earlier on.
Why is it density? Because it's kind of striation-like features, filamentary features.
This one?
Well, yeah, like pretty much everywhere. Well, I mean, I guess there you could say that this is some turbulent eddies, but in the upper right.
Yeah, this one is quite different from the other 3 cases. This one, because of the strong wind, the accretion is actually not driven by the turbulence. It's driven by the wind. You actually do not form well-defined circle at the disk, because this is sliced. This is actually showing that there are very strong spiral structures inside the disk. And those 3 have well-defined, more like a traditional disk is the rotation support. And the three of those three is actually the dominant, the accretion is the most dominant by the turbulence, not by, there's no wind. There's no magnetic centrifugal wind. The only wind coming from the last one, the radiation driven wind.
Just to clarify, this sort of striational features are a projection or an integration of the magnetic fields.
In the projection of the slice, like if you look at the 3D, it's more like you have a spiral disk here, and then there's another feature with the shocks. Not in one plane, it's in 3D structures.
Is this the cut or is it the?
This is the cut. This is the cut.
Yeah, this is the cut.
How magnetically supported it is?
Yeah, I will show you. Yeah, it's basically here. So I'm looking at if you actually look at the vertical profiles of the 4 rungs, this is the vertical profile of different pressure component. So the black line is the gas pressure, the green line is the magnetic pressure, the red line is the radiation pressure, and also I plot the product component of the kinetic energy, essentially the low VR square, low V theta square. And for the 3 rungs, you can see that the magnetic pressure near the midplane typically order of magnitude larger compared with the others. But then this one is the radiation pressure supported in this near the midplane. You can see that the radiation pressure is larger than the others. The gas pressure is always very small for AGN conditions, and is expected. The temperature is too low. The kinetic part actually is interesting. For this one, you can see that the kinetic energy is actually comparable to the magnetic pressure near the midplane, and that is what I said. That for this rung, this is the magnetic centrifugal driven wind rung. You get a very strong spiral shock near the midplane, and you create a very strong radial and the mutual velocity. This is not due to the turbulence, not due to the small scale like turbulence that you think about. And this is what I mean by the density. If you look at the density distribution, this is basically showing the density at 2 different radii for all the 4 rungs. The magnetic pressure dominant rung, typically you will think that is much more extended. That's not true if you look at the mass, like where the mass is. For example, for this rung, with the magnetic pressure support, this is the magnetic pressure supported rung, you still have a like density scale height, really only 5%. Like if you do the mass weighted height of this rung, the actual one is still only a few percent. But they have one extended tail. Once you drop below the central regions, the density drops much slower. So that in that sense, if you ask where the photosphere is, the photosphere is very far away from the midplane. So in that sense, the photosphere height is very thick. But that is different from the location where the most mass is. And that's very important because if you ask, given the mass accretion rate, right? The mass accretion rate again is the sigma times VR. And in the region where the density is so high, the inflow speed is actually much smaller compared with the inflow speed of the surface regions.
In the lower left simulation, which is radiation pressure dominated, do you
Yes.
see any evidence for the thermal instability?
No. So the M dot is also very high. If you look at this, is the 3 times Eddington. So the thermal instability typically, at least in the radiation dominant case, you typically happen like below like 30% of the Eddington. Once you're above that, the radial advection become more important. So you typically do not have that mode.
Okay.
And then I will show that for this one.
Basically, energy transport becomes non-local. That you are.
Yes, you have a radial, right. And that is actually interesting plot I'm trying to analyze where the accretion happens. If you look at basically the accumulated mass accretion rate as a function of theta. So these are for a given radius. I'm plotting like accumulated m dot as a function of theta in the top panel, and then the corresponding optical depth from the rotation axis at the bottom panel. So if you look at the 4 different rungs, and ask like half of the m dot the accumulate, you can see that all the rungs, the half of the m dot happens like at least like 10 degrees away from the midplane. But only in the low m dot wrong, this happens in the optical thin regions. If you look at optical depth, because the total optical depth is much smaller, and then the most of m dot for this wrong happens in the region when the flow is optical thin. But for the other wrongs, even though like half of the m dot happens also away from the midplane in the sense of the absolute value of the latitude, but they are still like optical thick for this wrong, for example, and optical thick for this wrong when the total accretion rate is high. So in that sense, that all those wrongs, doesn't matter if the magnetic support, the radiation pressure supported, they all have some extent of surface accretion, and they will call that. But not all the surface accretion actually in the optical thin regions. And actually in the case when the accretion rate is high, majority of them still happens in one optical thick part of the flow. Okay, in the last 15 minutes, I really want to get the key point I want to show the spectral. So I think that all the simulations, if you really want to say like which wrong is actually giving you the reality of AGNs, so you want to calculate the spectrum of the disk, including all the opacity in the self-consistent way. So we're basically using the multi-group module that we have in the Cine++, probably later in the Cine-K. And the opacity we take from the Los Alamos, the top opacity. So basically what we are doing that we divide the frequency space. Remember, this is the T0 correspond to roughly 10 EV. So we cover from like basically like 0.1 EV to like 10K EV, logarithmically with like 12 frequency groups. And then with another group cover from 0 to this, and another group from this to infinity. So divide the whole frequency groups with a total of 14 groups. And then for each groups, you can calculate you can get the loss mean opacity and the Planck mean opacity, nicely provided by the Los Alamos group. Some of the features, I just give you some examples of what opacity will look like. So the different colors show different frequency groups. The black are the low frequency groups, indicated by the numbers. The red are the high frequency groups, basically the KUV and above. And the different style showing the different density. And the opacity is showing the function of temperature. So you can, for the Planck mean, for example, for some of the high energy like a KUV and above, you actually get very large, actually the loss mean and the Planck mean. Actually, for the essentially get an X-rays, a very strong absorption opacities. So which is nicely captured by all the multi-group approach. Okay, so spectrum. So you can ask me the details of how to calculate that. But if you take the flow, we basically do the grid calculation to a steady state, and then we start with the 14 frequency groups. And then retain your broadband spectrum. Again, we definitely do not do a lines, but you can get an idea of the broadband from like 0.1 EV to like K EV part. And look at the spectrum for the 4 different wrongs. It's very clear that you have a more like thermal-ish peak centered around like 10 EV, could be slightly lower, slightly higher. And that is because the temperature of the disk. The temperature of the disk for this radial range and the black hole mass we chose is roughly like 25K-ish. So you have a thermal peak around this part as you would expect. But the most interesting is that if you actually look at the high energy part of the photons, if you try to fit it with the black body, the spectrum will drop much faster. But then for all the 3 wrongs, you get a tail, roughly if you try to fit a shape with a slope vary between like -1 and -2-ish. And for this lower m dot wrong, so I have 2 lines here. The black line is the spectrum, if I include everything also coming from the final regions, which is really not that reliable for those simulations because we do not include all the way to the east coast. But even when we exclude the final part, then this wrong, that means if you only consider photons emitted from the main body of the, main body of the disk, the low m dot wrong essentially do not have this non-thermal tails. But then the other 3 wrongs, the non-thermal tail is pretty robust. Well, the question is that where the high energy photon coming from? There are several mechanisms have been proposed in the literature to explain the non-thermal emissions coming from the disk. The number one is the thermal Compton, as I mentioned earlier. This is the mechanism also explain the hard X-rays. And that essentially that you have a thermal emission of the electrons, and you have a low energy photon come in, and then you can gain energy with photon coming out. But one important result of the thermal Compton is that the spectrum shape coming from this process depends on the so-called Compton Y parameter. And that is essentially like the optical depth times the temperature of the gas divided by ME square. And if the time is essentially the time taken for the photon to diffuse through the gas. If you take the diffusion, that essentially proportional to the optical depth square. If you put everything roughly, the temperature divided by 6 × 10⁹ K and the tau square. And if you look at the sum of the simple calculation of the Compton spectrum for different tau, and the Y parameter essentially for this particular setup is 10⁻⁴ times tau square. So for this blue line, the Y parameter is Y small. For the this black line, the tau is Y is much larger than 1. You can see the spectrum shape will depends actually sensitivity on the Y parameter that you have. And that's why I say that if you try to use this to fit the soft X-ray spectrum, you need a particular tau so that you get a Y to get the right spectrum shape of the photons. Another mechanism is the so-called bulk Compton due to the turbulent flow. And this mechanism, it just say that the random motion of the gas to scatter the photons is not coming from a thermal motion of the gas. It's instead actually coming from the turbulence of the flow, so that you need to have a supersonic turbulent velocity to exceed the thermal gas. This is actually basically the Fermi mechanism to accelerate the cosmic rays. It's basically proposed at the same time when Roger Bamford and others working on the cosmic ray acceleration. And this can happen, people think of this can happen in AGNs because the radiation sound speed can be much larger compared to gas sound speed. The temperature of the gas is very low. So in principle, you could have a turbulent velocity that exceeds the gas sound speed in AGN conditions. So you can have this mechanism maybe working. But one caveat that this requires the photons to scatter through all the turbulent eddies back and forth. So you have turbulent eddies, and then the photon need to scatter across those regions so you can experience all the motion of the flow. So that already tells you that this will be most effective when the photon mean free path is not that small. And that is basically the formula at the end of the day could come up with the effective temperature proportional to the turbulent velocity kinetic energy of the gas. But then the function also depends on the optical depth. When the optical depth is high, and this will be significantly suppressed. So this will be most effective really only near the surface of the disk when you have a supersonic turbulent velocity. The last one that I think is also developed at the early time when Roger Bamford was working on those cosmic ray accelerations. He also realized that if the flow is actually very thick, the photon energy can also be boosted if you have a large-scale converging flow. There is not a small-scale turbulence in the disk, but instead, for example, in this paper, the Penn Bramford 1981, they're thinking about just a 1D spherical symmetric inflow of the super Eddington accretion disk. When the photon is emitted here and carried with the flow inwards and get compressed. But if you have the right condition, the photon get boosted and then diffuse out with the flow. The spectrum of the photon emitted from this kind of case can be non-thermal. And the requirement you need is that is the most effective when the optical depth is order of CLV. That means the time for the photon to diffuse out of the system is roughly the time when the photons experience one direction of the flow. So you can get the converging effect of the velocity field. Another thing, the one nice feature is that the spectrum shape of the photon in this mechanism is not sensitive to the detail like object depths, the Y parameter. Instead, the final spectrum shape is actually most sensitive to the velocity profiles. Basically, how quickly your convergent flow, your velocity will increase during the time before the photon diffuse out of the systems. At the same time, they also require the convergent velocity to be larger than the electron thermal speed. So this is one different conditions, but give you a very almost universal prediction of the spectrum shape. For example, if you have free fall speed, when the velocity is proportional to R.5, then the spectrum shape mu of mu will be basically -1. So that is an interesting condition that almost independent of the details of the flow conditions. Is that what's going on? So I think the last thing that from the multi-group calculations, you can actually plot the spatial distribution of the high energy photons. So what I'm plotting here for the two laws, for the place where the high energy photon in the non-thermal tail are produced in the disk. So you will see that for this round, because the temperature near the midplane is too small, so the thermal emission will not give you anything. But the high energy photon really come to the place slightly away from the midplane when the gas is flowing much quicker. And then the white line that indicate the total optical depth from the polar regions. So this is the optical depth 1. This is the optical depth like 1000. So this is also happens in the region when the optical depth is actually order of the COV, not the optical depth photosphere, for example. And for that is true for both cases. So for example, for this one, the gas temperature is slightly higher, so you get a little bit of thermal emission from the midplane. But most of the high energy photons is also coming from the region away from the disk midplane. Another thing you can check is that for the multi-group approach, if you completely turn off the Doppler effect due to the velocity, basically due to you can turn off the acceleration because of the convergent flow, and you can find that the power law shape basically is gone. And that is a nice confirmation that the non-thermal tail is coming from the velocity of the flow.
So this is a bulk convergent flow.
Yeah. That's what I'm trying to say. Is that the bulk convergent, the gas is flowing in near the surface when the velocity is larger than the electron sound speed.
And then the exercise on the next slide is you turn off
You turn off the velocity. You basically turn off you just capture the thermal emission of the third multi-group, but you do not account for the frequency shift due to the Doppler effect.
Okay, so there is no Compton basically.
Yeah, there's no Compton basically.
Okay.
If you do not do that, then just a nice confirmation. It's nothing special about like the funnel or something that contribute to the non-thermal tails. Another nice confirmation that you can look at the vertical profile of say like 100 RG and look at different velocity component. For example, the green line is essentially the electron sound speed scale with the C, and the different black line is the radial velocity or turbulent velocity of poloidal velocity. And you also find that as I mentioned, right, the density is strongly peaked near the midplane. There, the inflow speed is actually pretty small, right? If you look at the V of C, it's like 10⁻⁴ of the speed of light. So near the midplane, the velocity is too small to do anything about the Compton. But once you're above the midplane, above certain regions, then the inflow speed start to exceed the electron thermal speed. And actually, if you look at the location, this is also the location where the high energy photon is essentially coming up in the previous slides. Another thing you can check, you can look at the radial profile of the inflow speed for fixed latitude. Even though the inflow speed is much smaller compared with the free fall speed, but the profile as a function of the radius is actually not that far away from 0.5. And that is another reason we actually pretty happy that this kind of velocity shift, if you use a formula from the Bamford, you will get the same spectrum shape. Yes.
So it looks like the turbulent fluctuations, which are the dashed lines, it looks like, are roughly the same amplitude as the inflow. So is it clear which one Is it both or is it one or the other? Is it turbulent comptonization or?
The turbulent Comptonization cannot do that because the upper depth too high. The turbulent Compton, the formula,
Right.
if you try to rely on the turbulent, yeah, the 1,000, there are the reduction factor. If you're 1,000, that means that what you need is the turbulent velocity at the scale of photon mean free path. This is turbulent velocity of the scale of the disk. If you actually ask turbulent velocity in the scale of the photon mean free path, is much smaller. I'm almost out, so I think just put a summary here. So I think it's interesting. I think do not forget about spectrum. I think that's the key message. I think you can make up all the disk model. I think it's very important to compare the spectrum with the observation to see what is going on, what is the model to describe a reality. Thank you.
Very much, Yan-Fei. We have got maybe a couple of minutes for questions before lunch. And if so.
So in the end, this X-ray access, is it coming from this, bulk comptonization of the convergent flow on the surface of the disk? Is that your interpretation?
Yeah, that's what I'm trying to say. Yes. So that is what I'm trying to say, that the thermal the 10 EV bomb is from the thermal emission, but then this bulk count, because of the convergent flow, give you the non-thermal tail. And that require you this kind of disk structure that more.
In the observational thing that you showed in the beginning, I think the peak was not at around 10, it was more
It's a
like
different background mass.
100. Oh, I
The
see.
now line for the one I showed for 10 to 7.
That was a lower mass.
Yes. There's another one, the PHEL 0.6 something. If you look at 10 to 6, 10 to 8 on my spectral, then the peak will shift to.
Down, okay.
Yeah, this is more like quasar. I think this is the conventional quasar typical spectrum. So this is the 0.1 keV. This is 10 EV-ish.
Oh, okay, so that's.
Yeah, if you go to 10 to 8 on my spectral like quasar, you have this, yeah. That's why I believe that the thermalized thin disk is not too long. You cannot completely abandon that. Because if you forget about, if the disk is not thermalized, I don't think you will even get this part, the peak of the thermal. Yes.
What about X-ray binaries? As you pointed out, they're not there.
I think binary, the issue is that is very likely the gas temperature is so high, the inflow speed, if it doesn't exceed the electron sound speed, then you will not get this. So that is another difference between the X-ray binary and the AGNs. I mean, this mechanism will not work for X-ray
Still very
binaries.
radiation pressure dominated, but you're saying they're both sort of the speed of light, both the gas.
Yeah, because
and the radiation acoustic speed or.
Yeah, because the radiation pressure is not too large compared to the gas sound speed for X-ray boundaries. And then the typical temperature is already 10 to 7K and above. And the electron sound speed need to be a square root of 1800 or something on that sound speed. The electron sound speed is pretty large in X-ray boundaries. And then only the AGN, the temperature is only 25K. So you have this scale separation for this to work.
Alex?
Yeah, I was curious if you've looked at, say, radial emissivity profiles compared to simple accretion disk models, because there's, for example, these micro-lensing observations that suggest.
Yeah, our radial range is too small. We at most get a factor few in radial part. Maybe one day if we can go from ISCA all the way to 100, then we can really do that. So far, it's very hard to compare because if you're wide enough range, you can fit anything like a power loss flow.
Fantastic. Well, we're past the hour. You can check out Yan-Fei's schedule to see if there's any meeting slots left. You're around for a little bit this afternoon, so please do check that out if you want to have a chat. Otherwise, let's head to lunch and thank Yan-Fei again.
Thank you.